Morning, everyone. Today I will be presenting my project title Simulation-Based Analysis of Thermal Barrier Coating Applied to Combustion Chamber of the Diesel Engine. This work is focused on understanding how ceramic coating, especially yttria, stabilized zirconia or YSZ, can significantly improve the temperature retention and overall performance of the diesel engine using the ANSYS simulation. So our agenda will be understand the introduction, problem definition, our objective for the project, literature review, methodology, and ultimately the conclusion. So, in the diesel engine, major share of the combustion heat is lost to surrounding components like the piston crown, cylinder liner, and cylinder head. And this loss not only reduces the thermal efficiency but also increases the fuel consumption. So, with the advancement of technology and material science, thermal barrier coating have become a powerful solution, and these coatings act as an insulation layer inside the combustion chamber. Talking about it, to understand why coatings are needed, we must look at how heat travels in an engine. So heat is transferred through the conduction, mainly through the piston and cylinder walls, convection due to the heat loss in by the gases in the circle which are circulating, radiation from the combustion flame. So the combustion chamber and the piston liner interface are the hottest region. So our objective is to minimize the heat escaping through the surfaces and retain it where it contributes to the better combustion. So the problem is that the diesel engine face a fundamental problem. That is, they lose too much of heat through exposed surfaces. So what does this mean? This lead to lower combustion temperature. Secondly, reduces the thermal efficiency, increases the fuel consumption, and lastly, it additional stress or the engine components also acts upon it. So our challenge is how can we retain more combustion heat without damaging the engine? Therefore, the project objectives include analyze the effectiveness of YSZ, that is yttrium stabilized zirconia thermal barrier coating in reducing the heat transfer. Study how coating influences the temperature distribution inside the engine and also to determine the optimal coating thickness in order to reduce the thermal stresses. Here's the literature review that is done by all the authors and other people in this field of study, and this ultimately helps us to guide our project well. So our methodology follows the structured engineering workflow. First will be the material selection, that is why I said that I have chosen for its low thermal conductivity and the high stability. Next will be the CAD modeling, where detailed geometry of the piston and the cylinder liner will be created. Third, simulation setup includes boundary conditions, material properties, and the heat loads applied in the ANSYS workbench. Fourth will be the simulation, like running the simulation. Multiple coating thickness scenarios are analyzed. Next and the last will be the temperature distribution, that is heat flux and the heat balance changes the studies. So it will be a workflow. Next is the characteristics and the material properties. So why we have choose Y and Z. The reason being the first is it has very low thermal conductivity. So it will keep the maximum heat inside the chamber. Excellent thermal shock resistance, high melting point, and vast compatibility with the metal substrates due to its thermal expansion coefficient. So compared to the other ceramic like alumina or silicon carbide, YSZ provides the best balance of insulation and durability for the internal combustion engines. So these are the TVCs we can use, and the material selection includes the lower thermal conductivity, high expansion, good erosion resistance, all these. So this is the proper table for the same. Here comes the engine reading. For the calculation and simulation conditions, we used Cooper diesel engine with the following specifications. Here the brake power, rated speed, number of cylinder, bore, stroke, and compression ratio is given, along with the mechanical efficiency and everything. So these specifications form the boundary conditions used in our thermal analysis. We have performed a complete heat balance analysis. So the fuel consumption, cooling water flow rate, exhaust gas heat were used to compute few of the things. So these are the calculations which are used to calculate ultimately the heat carried away by the cooling water, heat lost through the exhaust gas, brake power output, and ultimately unaccounted heat. Unaccounted heat includes the heat apart from the three, that is brake power, heat in the cooling, and heat in the exhaust gas. So our aim will be to reduce as much as unaccounted heat so that maximum heat retains inside the combustion chamber. As you can see in the table that here the supplied heat is 15.312 apart, and so from the total heat, the four parts where the heat is gone is calculated, and this is the percentage of the heat transfer for the uncoated piston. So here we have not applied any TBC coating on it, and this is the percentage of the heat flow. Next is the here we show the uncoated and the coated simulation model. So this is the uncoated model which has a direct metal to gas contact leading to the high heat conduction. This one is the coated model which includes the YZ layer on the piston crown, and besides is the cylinder liner, and this layer acts as an insulation barrier reducing the heat flow into the metal. This one is the meshing that is done in ANSYS workbench. This is the temperature distribution of the piston. So simulation results clearly shows that the coated piston and the liner surfaces maintains higher temperature compared to the uncoated ones. And at the same time, the metal substrate remains protected because the coating absorbs and redistributes the heat stress. So um, as we can see, we have done the same calculation for our coated piston as well, this the one that we did for uncoated one, and we have found the same parameters, that is heat in the cooling, heat in the exhaust gas, and the brake power, and the unaccounted heat. And this is the table for the coated assembly. As you can see over here, the exhaust gas temperature is as a percentage wise is increased as compared to the uncoated one. Here is the percentage breakdown for the same. So the reason being, when the YSZ has very low thermal conductivity, so it blocks the heat from flowing into the metal components and cooling system. So this means that more heat stays inside the combustion chamber and less heat escapes into the cylinder walls, piston, coolant, and lubricating oil. So the combustion chamber remains hotter for the longer duration of time. That's why the amount of heat inside the combustion chamber in the exhaust gas is more as compared to the uncoated one. So this is the comparison between the coated and the uncoated assemblies. As you can see, the exhaust gas temperature increases by 20 to 50%. Heat loss to the coolant decreases. More heat remains inside the cylinder, and the uncoated heat reduces significantly. So ultimately, these improvement translates directly into the higher engine efficiency and the better fuel economy. This is the temperature distribution, and this is the graph between the temperature distribution and the thickness of the coating. So to conclude, BioZ thermal barrier coating significantly enhances the thermal performance of the diesel engine components. The coated piston and the liner retain more heat, improve combustion efficiency, and reduces the cooling losses. So the optimal thickness, as we can see, there were many thickness like 0.2 mm, 0.4 mm, 0.6 mm, zero point 0.8 and 1 mm of the thermal coating is done. The optimal thickness or is 0.6 mm, after which the improvement level has increased. So this analysis shows that TBC can contribute to higher thermal efficiency, low fuel consumption, and higher engine life, making them a promising upgrade for modern diesel engines. Yeah. Thank you very much. And these are the references that I have taken for my studies. Thank you.